This is lesson 4.3. Today we're going to talk about rotation. So rotation is still a congruence transformation. In a rotation, points are rotated about a fixed point, which we'll call the center of rotation. If the point is the center of rotation, then the image and preimage are the same point. It wouldn't move. But if the point is not the center of rotation, then the image and preimage are the same distance from that center. So if the A is the preimage, and I'm rotating about point C, and A prime is the image, then AC and A prime C are the same distance. And the angle formed by connecting the preimage to the rotation point to the image is our angle of rotation. You can rotate any number of degrees. You could rotate 2.3 degrees if you'd like. We are going to focus on multiples of 90. We're going to rotate 90, 180, and 270. Unless they specify, all rotations are considered counterclockwise. I hate this picture. I meant to change it. But the opposite of way a clock would normally go, right? You're going the opposite way of the clock would be counterclockwise. So if they just tell you to do a 90-degree rotation, they mean counterclockwise. They might also just tell you it's counterclockwise. I'm going to abbreviate to CCW because it's a very long word and it's incredibly annoying to write. Otherwise, if they tell you specifically, it could be clockwise, and that's following the hands of a clock the way you would normally go. There are equivalent rotations. So 90 clockwise, right, if I started here, 90 counterclockwise, and I went this way, that's the same as if I started here and went 3 turns, or 270, this way. So they should always add to 180. 90 and 270, 180 and 180, 270 and 90. Our rule for 90-degree counterclockwise rotation about the origin. If I notice my original point was 5, -2, and now I have -2, 5, I have the same numbers, but they flipped. So one thing that happened is y and x switched places. And then the first spot changed its sign. So that would be -y, x. For 180, if I look at my pre-image and my image, I have the same numbers in the same spots, so it's still x and y, but both of them changed their signs. So that's -x and -y. And then for 270 counterclockwise, I again have the same numbers, but now they're switched, so it's y and x. And now the second spot changed its sign, so that's y -x. So I like to make myself this little chart of my counterclockwise numbers, the rules, and the equivalent clockwise rotations. We knew that 90 and 270 both flipped. In 90, which comes first, the first spot changed sign. In 270, which comes last, the last spot changed sign. And 180, when you hear of a person doing a 180, they're doing the opposite of what they did, so we're going to do the opposite of both variables. For example 1, we are given our coordinates. We want to graph the image after a 180-degree counterclockwise rotation about the origin. So I'm always going to list my points first because that's the rule that I'm using. So 180 is -x, -y. So that just means I'm changing every sign here. P prime would be -1, +1. Q prime would be -5, +3. And R prime would be -5, +3. Uh-oh. Those shouldn't say the same thing. Let's see where R really is. 3, -7. Let's try this again. So R prime should really be -3, +7. So now I can graph -1, 1 for P prime, -5, 3 for Q prime. Something is fine. We're good. And R prime is at -3, 7. It makes sense that if I'm going 180 degrees, that's going to be 2 90-degree turns or 2 quadrants that we move. So I went from here to here to here. That's my 180. It's opposite of what it was. In example 2, we want to graph the image after a 90-degree clockwise rotation. So 90 clockwise is equivalent to 270 counterclockwise. And that rule was y -x, right? They switch places. Second one changes sign because 270 came last. So the way I like to do this, at least until I'm comfortable with the rules, is I'll start by doing the switch. I'll keep the signs exactly as they are, but I'll do the switch. So 3, -6 first. And then I'll focus on changing the sign of the appropriate number. So first we'll flip for a -2, and then I'll change the appropriate number. And then n is -3, -5, and then I change the appropriate number. So L is now at 3, 6. Sorry, L prime is now at 3, 6. M prime is at 4, 2. And N prime is at -3, 1, 2, 3, 4, 5. And this again makes sense. The original was in 2 different quadrants, right? It was in quadrants 1, 2, 3, 4, 2, and 3. And we moved this point 1 quadrant, and we moved these points 1 quadrant. Each went 1 turn this way. So for the try, you don't even have to graph them. If you'd like to give it a shot, pause, and the answers are posted online. In honors, we're going to rotate around points that are not the origin. So we're going to have to do more work for problems like that. And this is going to be what we do. We're going to call it SRA. We're going to subtract the center of rotation from every point. We're going to use the normal rules, and then we're going to add the center of rotation back. So SRA. Subtract, rule, add. So if these are my original points, and on a graph after a 270 counterclockwise rotation about -1, 2. So this is my center of rotation. So I'm going to start by listing the 3 points, the 3 ordered pairs, and I'm going to take away, subtract -1 and +2. So minusing a -1 is adding, and then -2. So each one's really going to get +1 and a -2 for my subtract row. So this is going to become 3, 6, this is going to become 6, 1, and this is going to become 7, 4. Now I'm going to apply the rule. So 270 counterclockwise, y -x. We're going to get 6, 3, change the sign, 1, 6, change the sign, 4, 7, change the sign. And then the last thing we're going to do is we're going to add it back. So now we're going to follow exactly these signs, a -1 and a +2, a -1 and a +2, a -1 and a +2. That gives me end results of P prime is 5, -1, Q prime is 0, -4, and R prime is 3, -5. So 5, -1, 0, -4, and 3, -5. Oop, that's a bad line. It's a little harder to judge based on the picture if we were totally right. The things we should be looking for are making sure that the pre-image and the image are the same shape, the same size, and that it's still moved in the direction we thought it should. So 90 degrees clockwise is the same as 270 counterclockwise, so 1 turn this way, it looks like we did it correctly. Here is a try problem. I would highly recommend trying this one. Pause it if you'd like now. The answers are posted online. So just like we had line symmetry with our reflections, we also have rotational symmetry with our rotations. So rotational symmetry is if you can turn the picture and make it still look exactly as it did when it started. All right, whatever point you're turning it about is going to be called the center of rotation or center of symmetry. And we can rotate any number of degrees between 0 and 360. The angle of rotation is also called the magnitude, and I will be using both words interchangeably. So the magnitude is the smallest angle through which a figure can be rotated so that it maps onto itself. The largest angle of rotation, or the largest magnitude, can be 180. You cannot have an angle of rotation or a magnitude of 360 because that would mean that you had to turn the figure completely around before it ever looked the same, and then it just doesn't have rotational symmetry. The number of times you turn the figure is the order And we can actually find the angle by doing 360 divided by the order. So again, if 180 is the largest angle of rotation that it could be, 2 is the smallest order that we can have, because 360 divided by 2 is 180. So we want to state whether the figure has rotational symmetry, and if it does, we're going to state the order and the angle of rotation. So right now, we're looking at this picture. I'm going to duplicate it. We're looking at this picture, and we want to rotate it so that it looks exactly the same. So I'm turning it, and right now it looks the same as it started, right? It looks exactly the same, but the green dot's on the bottom when it started at the top. So this is once already that it's looked the same. And then if I keep going, on the second turn is when it looks like it did with the green dot at the top. It's back to its original position. So this would mean that it has an order of 2. So the angle of rotation would be 360 divided by 2, or 180 degrees. All right, let's duplicate this one. So here, again, I'm starting with the green dot at the top. I'm turning it. This is the first time that it looks the same. I keep turning it. This is a second time that it looks the same. Here's a third time. Here's a fourth time. And then back to the original green dot at the top is the fifth time. So this actually has an order of 5. Which means that the angle is 360 divided by 5, which is, I want to make sure I give you the right number because my head's not working right today, 72 degrees. For this last one, I'm going to turn, so that doesn't look the same yet. No, doesn't look the same. Doesn't look the same. It took all the way till the green dot went back to the top for it to look the same, which means this does not have rotational symmetry. So the easiest way to just look at a picture and know if it has rotational symmetry or not is, does it have equal pieces to it? Are those equal pieces equally spaced? So these 3 angles are all different measures, so that's why it didn't have rotational symmetry. In this, these 5 angles were all exactly the same, and they're all equally spaced apart from each other, and that's why our order was 5. This one, these 2 angles matched, and these 2 angles matched, and they're equally spaced from each other in that aspect. So this, if I wanted to call it, like, this had 2 points to it, like 2 narrow points. It had 2 big points, but it had 2 narrow points, so the order was 2. The number of legs or pointy bits or congruent angles, those are the things you should be looking for to determine what the order would be if you don't want to have to physically turn the objects. So then if you wanted to try these 2 and determine their order and angle of rotation, the answers are posted online. But that is the end of rotations.